Hello, my name is Bartolome Malagon Ramirez. In this project, I use Google Cloud AutoML to build a machine learning model that predicts the hourly electrical energy output of a combined cycle power plant. The dataset used includes over 9,500 hourly records with environmental variables and power output in megawatts. The task is a regression task on tabular data. Google AutoML handles preprocessing and tests multiple algorithms such as linear, tree-based, and neural network approaches, selecting them all with the lowest prediction error. The objective is to produce an accurate, interpretable forecasting model suitable for operational decision-making. AutoML automates data splitting, hyperparameter tuning, and algorithm selection. By default, the data is split into 80% training, 10% validation, and 10% testing, using a random stratified approach. AutoML simplifies experimentation while ensuring the best suited model selection. The task is to predict a continuous numeric target, which is the net hourly power output. The four input features are temperature, ambient pressure, relative humidity, and exhaust vacuum. Energy output in megawatts is the target that the model needs to predict. AutoML evaluated candidate models and identified gradient-boosted decision tree as the top performer. The primary evaluation metrics was root mean square error, which emphasizes larger mistakes by squaring errors before averaging. I also included mean absolute error, mean absolute percentage error, root mean square, logarithmic error, and the coefficient of determination to provide a complete view of performance. I trained two models to compare accuracy and efficiency. Model 1, which is the full feature model, used all four inputs to capture the complete environmental signal. Model 2, simplified feature model, used only temperature and exhaust vacuum, based on a feature importance analysis that I did, which showed these two dominate predictive power. This comparison demonstrates the trade-off between maximum accuracy and lower complexity and cost. Both models use gradient-boosted decision tree. The full feature model achieved root mean square error of 3.1 megawatts, mean absolute error of 2.37 megawatts, and coefficient of determination of 0.966, explaining about 97% of the variance and typically staying within 1% of actual output. The simplified feature model achieved root mean square error of 4.03 megawatts, mean absolute error of 3.18 megawatts, and coefficient of determination of 0.942, still explaining 94% of the variance while being lighter to train and serve. Here is the side-by-side comparison. The full feature model is better on every measure. Lower root mean square error and mean absolute error, lower mean absolute percentage error, and higher R squared. The roughly 25% lower root mean square error translates to tighter, more reliable forecast, typically within about 3 megawatts of the true output. In summary, Google Cloud AutoML efficiently evaluated multiple algorithms and hyperparameters and selected gradient-boosted decision tree as the best fit. The full feature model achieved root mean square error of 3.1 megawatts and R square of 0.966, delivering the highest overall accuracy. The simplified feature model remains a strong option with only a modest accuracy trade-off. For production forecasting, where precision matters, I recommend deploying the full feature model. Thank you for listening.